is This is chapter 5, number 3 in the real number system. This is section 5.3, the rational numbers. All right. In this section, you're going to learn about rational numbers. You're going to learn how to reduce rational numbers, convert them between mixed numbers and proper fractions. I like to say fractions bigger than 1. So this would be where the numerator, the top number, is bigger than the denominator, the small number. Express rational numbers as decimals, express decimals in the form of a over b, and then learn how to multiply and divide rational numbers, and then add and subtract them. And of course, then use the operations, the order of operations to manipulate them. And then apply the density property of rational numbers to solve problems involving rational numbers. So quite a big agenda. This is an ambitious section. I'm looking forward to it. All right, let's dive in. All right, defining a rational number. The set of rational numbers is a set of all numbers which can be expressed in the form a over b, where a and b are integers and b is not equal to 0. The top number that is called the numerator and the bottom number is called the denominator. Okay, so integers of the form a over b, where a is the numerator, b is the denominator. Some examples are 1/4, -1/2, 3/4, 5, and 0. You may be wondering, where is the denominator in 5 and 0? And so we can write those as rational numbers by putting 5 over 1 and 0 over 1. Reducing a rational number means that we can find a common factor of a times c and b times c and reducing it. In other words, those two common factors of c will reduce to 1, and so we are left with just the values of a over b. All right, so let's look at an example. So if we wanted to reduce 130 and 455 to lowest terms, okay, we're going to find the greatest common divisor, the GCD. That may sound familiar from a couple lessons ago. So the GCD of 130 and 455 using the factor tree, we have 2 times 65 and 5 times 13 equals 65. And then looking at 455, we have 5 times 91 and then 7 times 13. Okay. Looking at each of the numbers in the factors, we see a 5 and a 13 are in order. And so 5 times 13, or 65, is the GCD. Okay, that would be the C term in the previous slide. Okay, so writing those out then, we see that the 65s will cancel from the numerator and the denominator. And that then leaves, of course, 2 over 7. Okay, and so 2 over 7 is the lowest in lowest terms. In other words, another way of saying that is 2 and 7 are relatively prime to one another. Their GCD is 1. Okay. All right. Mixed numbers. Mixed numbers are a combination of a whole part and then a fractional component. So think of this as like dollars and then change, right? So you have $3.60. You would have $3. That would be the whole number. And then 60 cents would be 60 over 100, or 60 cents. Okay. All right. So we can convert that then to a whole number and a mixed number, or we can convert it into a fraction bigger than 1, often called an improper fraction. And to do that, you're going to take the numerator and multiply it by the whole number part. So if we're looking at the example here, 3 and 4/5, 3 times 5 gives you 15, and then you add then the exponent. So, or not the exponent, sorry, the numerator. So 15 plus 4 gives you 19. So then this number written as a fraction bigger than 1, it would be 19 over 5. Okay. Converting between these two kinds of numbers, between a positive mixed number and an improper fraction, that's what I just explained in the previous slide. So multiply the denominator by the whole number part, and then add the numerator of the fraction. All right. So here it is written out more explicitly. Sometimes the steps are helpful to see. So 3 times 5 is the 15, and then you're adding 4. So 15 plus 4 gives you then, of course, 19, and you're then dividing by 5 as the numerator. Okay. And again, another way to think about this is how many groups, how many equal size groups of 15 are there? And so just keep that in mind. If you're given something like this, what it's saying is, okay, so you start over here at, you go from 0 to 19, So how many jumps of 5 do I have in this? Well, I have 1, 2, 3 jumps of 5. So this is a distance of 5. That's a distance of 5, and then that's a distance of 5. And I just don't quite have enough to make it to another group of 5. So I have 1, 2, 3, 4 left over. And so I have, here are my 1, 2, 3. So this group right here is the whole number part. So in other words, there are 3 equal groups of 5 in there. So there are 3 equal groups of, and then what's left over is the 4 out of the 5 left over. And so that's how you can uncover or go backwards from a mixed number, or from a improper fraction to a mixed number. But always remember that the denominator is telling you how many sizes of equal groups do you have in the larger number. Okay, and that's what a mixed number is telling you. In this case, you have 3 groups of 5 in there, and then you have 4 ones left over, or 4 pieces left over, which is not big enough to make another group of 5. All right. I hope that's helpful, and hope that makes some sense of the connection between whole numbers and improper fractions and fractional pieces, or the operation of division. Okay. All right, let's move on. Okay, so here's what it's referring to in what we were just explaining, and how to convert. I just showed you with that other example, but let's just do it one more time for completeness here. Okay, so in this case, I have a group of, so here is 42, and here is 0. And so I'm looking at groups of size 5 again. So 1, 2, 3, 4, 5, 6. So I might need to make them a little bit smaller. Oh, I didn't make them right size. I need to be consistent with, I can change that, because I think those are all pretty close actually. So I have 1, 2, 3, 4, 5, 6, 7, 8, and then, okay, so here's 42. This is 42. So how many groups do I have? I have 1, 2, and in case you're wondering, how did I know that? Well, this is 5, 10, 15, 20, 25, 30, 35, 40, and I don't have enough to get over. So that's how I was counting. That's how I knew how many there were. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8. There are 8 groups of size 5. So each of these is a jump of 5. Okay. I think you get the idea. So each of these is a group of 5. And so when we get to here, there's not enough left over to get another group of 5. So if I look at, well, what's left over, then up to here, I have 40, and then I have 1, 2 more left over. So there's going to be a total of 8 groups of 5, and then there's going to be 2 more of that left over out of 5. Okay, so 42 out of 5. How many groups of 5 are there? There are 8 groups of 5 in there, and there's the remainder of 2 left over after that. Okay, so as a mixed number, 42 over 5 is 8 and 2/5. Okay. And again, if I wanted to go backwards, all I'd have to do is multiply 8 times 5. That tells you how many there are, and then add the exponent, or I keep saying exponent, add the numerator. Okay. Let's look then at this next part, rational numbers and decimals. Any rational number can be expressed as a decimal by dividing the denominator into the numerator. Okay, which is what we were just doing. But if we did that in the traditional sense, I'll do 8 into 5. So to convert this into a decimal, take 8 into 5, and then go, okay, well, 8 doesn't go into 5. So I'm going to add a decimal. And now 8 goes into 50 6 times. And that gives me 48. If I make that difference, then I get 2, bring down another 0 from here. And then 8 goes into 22 times. And so there's going to be 16. Subtract that, you get a difference of 4, add another 0, that comes down. Okay, and then 8 goes into 45 times. So 5 divided by 8 is the same thing as 0.625. Okay, you can also see that again, if we have, let's say, 0 to 8. Okay, so it's saying how many, oh, sorry, yeah, yeah, let's do that. Okay, and there's 5. Okay, so what it's saying is how many groups of equal size are there in 5? How many groups of equal size 8 are there in 5? Well, there's clearly not a whole because 5 is less than 8. Going back to our first example, our first lesson, right? So 5 is a smaller number than 8, so it can't be a whole number. So it's you can think of it as like a percentage, if you will. It's how much of if this was my whole, if this was my whole, right? This is my like my whole unit. It's from 0 to, let's say, 100, or 0 to 1. This would be percent in this case. How much is it? And what we found is it's about 62.5%. Okay, or it makes it up. So it'd be 62.5%, or it's almost 2/3 of 5 is almost 2/3 of 8. So there's almost 2/3 of a group size 8 in this calculation. Okay. And so they did that here in this example. Notice that when you're dividing by something like 11, you're going to get this possibility of the number repeating. And so in that case, then we designate the repetition by drawing a bar over the digits that start to repeat. All right. Expressing decimals as a quotient of 2 integers. It's good to know their place value. So anything to the left of the decimal is whole number. So ones, tens, hundreds, thousands, 10,000s, 100,000s. And to the right, it follows the same pattern, except for it misses the ones. And so it starts with tenths, which is like the tens here. Tenths, hundreds, thousands, 10,000s, 100,000s. And you can think of this as like powers of tens. This is 10 to the negative 1, represents the tenths. 10 to the power of negative 2 represents the hundredths, and so on and so forth. All right. So expressing the terminating decimal as a quotient, knowing this is really important since we are in a decimal system. Then this tells us then how to write each of these. So 7/10 is the place value here. So we can write that as simply 7/10. Here, the place value is in the hundredths place, right? This is in the hundredths place. If we look back up here, it's got 2 decimal places, so it's in the hundredths place. So we can start by writing this as 49/100. And then we can see if the GCD of these two, what's the largest value, and then reduce if necessary or if possible. However, 49 has just the one factor of 7, and 100 does not have a GCD where 7, so the GCD of 49 and 100 is 1. They're relatively prime to each other. And so in that case, this is in lowest form. And now here, notice that we're in the thousandths place since we're 3 decimal places over. So this is going to be 48 divided by 1,000. And now here, the GCD of 48 and 1,000 is not 1. And so we could reduce this as a decimal, should we choose to do so. Okay, but the important point here, of course, is to recognize then that the last digit, if that is all that there is represented in the decimal, then is the place value that we can use to write it as a fraction. Okay. All right. How to express a repeating decimal. So if we divide 3 by 2 or 3 by 1, you're going to get this value. And if we wanted to go backwards, we can use the results here to multiply that out. Okay, so that's what we're doing here. Since it's the 6 that is repeating, we can write that as an n equals 0.66666 forever. And then we can multiply that equation by 10 because it's in the tenths place. So multiplying that over by 10, you get 10n is equal to 10 times this. Well, that's 6 times our 0.66666. Okay, and then we can subtract the 2. You can subtract 10n from 9n and then divide. And that will, of course, give us 6/9, which has a GCD of 3. And so reducing those top and bottom by 3, you get 2/3, which is the 2/3. All right, multiplying rational numbers. Multiplying rational numbers means you just multiply straight across. So if you have A over B, and C over D, then their product would be AC times or divided by BD. Sorry. And this is, of course, assuming that A, C, B, and D are all relatively prime, so they don't reduce. If they do reduce, like in this example, you will still do the same thing, but you can reduce the number after the product. You can find the GCD of the resultant products and reduce. So negative 2/3 times a negative 9/4. Again, the negatives, we have 2 flip-flops, and so it's going to be an even flipping. So we'll end up on the right-hand side of the 0, which means this is a positive number. And then multiplying straight across, 2 times 9 is 18, 3 times 4 is 12. 18 and 12 have a GCD of 6. Canceling out the common factor of 6 reduces to 3/2, which we can write as a mixed number by dividing 2 into 3. Or you can think of it this way. Here is 3. How many? 1, 2. There is one group of 2 in there, and then if I wanted to go, here's 4. The next group of 2 would be here, so it's only half that distance, right? So it's one group, and then 1/2 of that. All right, so that's how to convert. Okay, and then dividing rational numbers is a similar idea. It is still the exact same thing. That you're trying to figure out if you have a number A over B. Let me draw the number line. Keep that consistent. Okay, so if you have a number over here, A over B. Now this could be like anything that we've done before. It's just a number. A over B is just a number. Okay, and what we're trying to figure out is how many groups of equal size are in this. So I don't know what C over D is, but this is pretend, for example, that it's this far. Okay, and if it goes in evenly, okay, this is one C over D, this is another C over D, and this is another C over D. So if it goes in evenly, if it happens to go in evenly, okay, then the result in this case would be like 3, right? But if it doesn't go in evenly, so let's say that C over D is like something like this, then what you're going to get is you're going to get, like in this case, you get 2, and this piece would be the remainder. So you're going to get a mixed number. In this case, C over D would be smaller than A over B, obviously. And in the other case, if C over D is bigger, kind of like in the 5/8 example, you'll get another decimal number because the result C over D is bigger than A over B. Okay, but hopefully this makes sense in the terms of you're just finding these equal groups of, kind of like before when we did the groups of 5, right? And we counted those. So each one of those is a group of 5. This is a group of C over D. And we're just counting how many are there, and then whatever the remainder is how much is left over. So that's actually what's going on. In practicality, what you get is this relationship. And I don't like to memorize things, but you often hear this as A divided by B, A over B divided by C over D. What you do is flip and multiply. What it's referring to is you flip over this second fraction and then multiply straight across. That is a result of the counting that you get from this process here. So I think an example is helpful, so let's go ahead and do that. So we have negative 3/5 divided by 7 over 11. So negative 3/5 divided by 7 over 11. Doing it this way, you flip over this fraction to 11 over 7 and multiply straight across. Again, there's only a single negative, so it's only one direction. So we're going to be in the negative direction. So this is negative 3 over times 11, which is negative 33, and then 5 times 7, which is negative 35. Okay. If we drew this out, here's 0, and then I have a negative 3/5. So I'm going to call this 1. I'm going to call that negative 1 because, again, this is pointing in the negative direction. Let's see, 1, 2, 3, 4, 5. Okay, so I'm going to call I'm gonna erase this real quick. And I'm going to call this -1. Trying to keep them, they're not exactly the same, but this is 1/5, 2/5, 3/5, 4/5, and then this would be 5/5 or -1. Okay. And this is saying 7/11. Okay. So 7/11 is a little over half. And what I could do is I could divide this up evenly and cut up all the little pieces. Um, and if I did that, I would see that there's 35 little pieces that I need to draw here in order to make them the same size. But it's roughly right about there. So this is 7/11, roughly speaking. And so it's asking how many of these are there in this -3. Oh, sorry, -3/5 is 1, 2, 3. So there's -3/5. Forgot to point that out. -3/5 is right here, and 7/11 technically would be negative, but we're talking about distance here. So this is 7/11 here. So and how did I get that? If you're wondering, 7. So if you think of this as like, this is about equal to 10. Okay, so this is really close to 10 and 7. So if this was 5/7, that would be exactly at a half, but 7 is bigger than the halfway point. And so if I increase this by 1, I'm increasing this by 2, which means that this is definitely bigger than halfway through. Okay, so that's how I got here. So 7/11 in distance is about here. And so if I look at this relationship, I'm asking how many of these are there in this, right? Well, 3/5 isn't as far as 7/11, so it's going to be a number less than 1, which is what is verified here. Okay, so that's just to kind of give you a visual of what's happening. And if we can figure that out in more detail, we would see that this is the result that we get. Okay, but the result isn't flipping and multiplying. All right, hopefully that makes sense. Adding and subtracting rational numbers is very similar. So what you're going to do is you're going to take the and get a common denominator. So if they have a common denominator, like in this case, you can just add straight across. Same as with subtraction, when they have a common denominator. When they don't, what you need to do is force a common denominator. So here are several examples where we're given the opportunity to add or subtract straight across. Notice here you convert into improper fractions first, and then add and subtract. When the denominators are not the same, then you need to get a common denominator, and to do that, you simply multiply by the LCD. Or sorry, I should say, in order to get the LCD, the least common denominator, you find the LCM, and then multiply each by the individual. So the LCM of 4 and 6 is 12. So you multiply here, in this one, 4 times 3 gives you 12. So you multiply top and bottom, because 3 divided by 3 is 1, so it's not changing the value of it. And so you get here 9/12, and then here you get 6 times 2 gives you 12. So you multiply top and bottom here by 2. So you get 2/12 and 9/12. And then now they have a common denominator. So now you can add them together. So 9 plus 2 gives you 11/12. All right. Let's talk about the density of rational numbers. If R and T represent rational numbers and R is less than T, then there is a rational number S such that S is in between R and T. What does that mean? It's just basically saying this, like, so here, so R is here and T is here. What it's saying is that there's always some rational number in between these two. And in particular, one way to think about that is, what about this point right here? This point right here has a special name. It's called the midpoint. The midpoint. And how do you find that? Well, we can call that R plus T divided by 2. And if we call that S, then we're always going to be guaranteed that there's at least one point in between them, because this is a rational number, and it is by design in between these two numbers. So there always exists a rational number, and that's what it's talking about. The density of them is that, and it doesn't matter what R and T are. You can always find a rational number in between those two numbers. In particular, one that's easy to think of is the midpoint between R and T, no matter how small these numbers get. All right. So here's an example illustrating that property. And then finally, solving rational numbers. A common application of rational numbers involves preparing food for different numbers of servings. Amount of ingredients needed equals desired serving size divided by the English is always a challenge for me sometimes. The recipe serving size, and then you multiply that by the ingredient amount and the type. So in this case, adjusting the size. So as typically it looks like you're having a party, you have a recipe that only makes so much. So you need to either scale it down or scale it up. In this case, a chocolate chip receipt for 5 dozen cookies requires 3/4 a cup of sugar. If you want to make 8 dozen, so here we're scaling up, right? We have 5 dozen and we're trying to make 8 dozen. Okay, so what do? You have the desired serving amount, that's 8 dozen, divided by the serving size, which is 5. And then you multiply that by the number of, or the required number of ingredients in the cup. So 8/5 times 3/4 then gives you the adjusted size. So you need 1 1/5 cups of sugar. Okay, so that's a really good example of how scaling up or scaling down occurs with rational numbers, especially in terms of baking. All right, hope that was helpful, and I will see you in the next video.